And I would also point out that this is the reason why you tend to see more C4 grasses in the tropics and more C3 grasses in the extratropics. Solar radiation. So, a couple key concepts regarding radiation. First is Rayleigh scattering. This is why the sky is blue. And basically, particles in the air, which are smaller than the wavelength of light, will tend to scatter that light in all directions, omnidirectionally. And it's not clear to me why that's connected to this spectral effect, but there is a strong spectral effect in that scattering, so that you tend to scatter a lot more blue than you do red. This is why the sky appears blue, because all that blue light is scattered, and that's what you see up in the sky. This is contrasted to me scattering, in which the particles are larger than the wavelength of the light that they're scattering. There's no spectral dependence here. And so, for example, with water droplets are much larger than the wavelength of visible light. And so when you see a cloud, you can see it appears white instead of blue or red or orange or whatever. And that's because the me scattering has no spectral response. It stays white. Or if it absorbs all the light, then it goes to black. So it's white to black for clouds. We consider two kinds of radiation. So plants take up solar radiation to perform photosynthesis, and then pretty much everything on the planet emits long-wave radiation. So short-wave radiation is emitted by the sun at, I think it was 6,700 Kelvin, and because the emission spectrum of an object is related to its temperature, as we went through with the equations that you don't need to memorize. But then we got into the more interesting stuff, the less physics, more botany. And first we talk about leaf temperature and energy budgets with the leaf in its environment. So what happens is as wind flows across a leaf, it forms this boundary layer due to friction with the wind, friction of the wind against the leaf. So as you get farther into the leaf, this boundary layer becomes thicker. A thick boundary layer doesn't transport much heat. It's pretty insulated. This boundary layer can become smaller with higher wind speeds, which is kind of sensible. Smaller leaves will have smaller boundary layers. If you have serrations on the leaf, then you'll decrease a smaller boundary layer. If you have lobes on your leaf, you'll decrease the boundary layer. Or if you have compound leaves. Why this is important is that as the boundary layer gets smaller, leaf temperature approaches air temperature. And this is important because what it means is that if you have a small leaf, like a needle leaf or a phylode, then that leaf can never be cooled below air temperature. So it cannot experience evaporative cooling. Evaporative cooling can be very important, especially for a large leaf. It's really fun sometimes on a nice, warm, sunny day to go out and start feeling the eucalypt leaves, because they're actually cooler than the air. And it's because of this evaporative cooling, because they have this big boundary layer. And so they don't get the heat from the air doesn't get down to the leaf, and they can cool it with the evaporation instead.